SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the course Advanced Thermodynamics and Combustion, Module 3, that is Thermodynamic Property Relations. In total, in this module, there are 5 lectures, and already we have covered the first lecture, that is thermodynamic functions and Maxwell's equations. In fact, we derived in the last class various thermodynamic functions and Maxwell equations based on the understanding of differential equations, and that differential equations were in the form of ordinary or and partial differential equations. We are now in the lecture number 2. Here we are going to apply these Maxwell equations for thermodynamic processes. The first part of this is that we are going to derive the property relations for a phase change process. So, in this lecture, that is property relations for phase change processes, these are the some contents. First of all, we will discuss what we derived in our last lectures, what are the different property changes that are associated in the form of Maxwell's equations and other relations. And for phase change processes, two important equations are predominantly used. One is Clapeyron equations, other is Clausius-Clapeyron equations. In fact, both the equations are same, more or less same, but with certain approximations, different concepts were developed. Now, after deriving these Clapeyron equations and Clausius-Clapeyron equations, we will be discussing its applications with respect to phase diagrams. The phase diagrams normally refers to pressure temperature projections, where we distinctly decide about fusion curve, sublimation curve, and in these curves we will see that how these two equations are applicable or vital. Now, let us revisit our previous lectures where we derived the thermodynamic property changes. In total, there are 16 property relations that were obtained by using the concept of exact differentials. Then we introduced Maxwell's equations, and through these Maxwell equations it is possible to allow the relations or develop the relations to allow the changes in entropy, internal energy and enthalpy. And in fact, these properties values can be measured or can be evaluated from the measured data. That is most important thing. Normally the measured data are pressure, density and temperatures. Now, through this measured data we are going to develop equations, and that equation will give you other property values such as changes in the entropy, internal energy and enthalpy. Now, after deriving these equations, we are now going to consider the phase changes processes and single phase regions, and basically we are applying these equations in two situations. One is for phase change case, other is single phase case. The phase change case may be solid to vapor or solid to liquid or liquid to vapor and vice versa, and single phase region means either it is in solid or it is in liquid or it is in the vapor. So, in total there are 16 relations, and to summarize these 16 relations, what we can say pressure, temperature and specific volume or density, these are the measured data, and properties that need to be evaluated are internal energy, enthalpy, then entropy, and of course the Gibbs function G and Helmholtz function Xi. In fact, with through these basic relations we have additionally Maxwell relations and some other relations as well. So, in fact, these relations are very generic and mathematical in nature, and since they are in mathematical nature, they are applicable to all kind of thermodynamic processes, but only thing is that these equations needs to be simplified based on the requirement. Now, one such situations or requirement in our case is a phase change process. So, the most important equations that allows us, that means which is derived from all 16 thermodynamic relations, one of them is the Clapeyron equations, and in fact it is applicable for a phase change processes, and we will see that how these Clapeyron equations help us in simplifying certain analysis. Now, when I say phase change processes, it involves three things. One is vaporization, second one is sublimation, third in melting. So, solid melts to become liquid. Sublimation means the solid goes directly to vapor. Vaporization means liquid goes to vapor. So, we are going to see that how this Clapeyron equations is useful for this phase change process. Even I am repeatedly telling that the measured data are pressure, specific volume and temperature on a PVT surface, and the properties that needs to be calculated are typically entropy, specific entropy, internal energy and enthalpy. Now, if you look at these equations, in fact this is the TDS equations, that is dH is equal to TDS plus BDP. We all know that since it is in equations and all these numbers are properties, so it is applicable for all the processes, whether it is reversible or irreversible. And if you are going to apply for a phase change processes, so for a phase change processes we can say that dH becomes TDS, because in a phase change processes normally temperature or pressure do not change. So, dP, the second term goes to 0. So, this equation now simplifies to dH is will be TDS. Now, from this equation, since it is in differential form, so with finite value we can write or simplify these equations taking ds close to delta S, and delta S we are finding out from Sg minus Sf. So, Sg stands for specific entropy in gas phase and Sf stands for specific entropy at the liquid phase, and corresponding value of enthalpy would be Hg and Hf. And since the phase change process happens at a constant temperature T, so T remains constant. So, this expression helps us that from the enthalpy values one can calculate entropy values. And in fact, we all know that enthalpy is also U plus PV. So, from this enthalpy value one can also calculate the internal energy change, that is Ug and Uf. Okay. So, this is the significance of equations. Now, let us see how we can come back to the Clapeyron equations. So, just refer to our figure, that is pressure temperature plot for a pure substance. What we have here is that this plot talks about two important points. One is the triple point, we normally call it as a TP, other is the critical point CP. So, there is a continuous curve and we call this as a locus of the saturation states. So, it means that across the line the state of the system is liquid and vapor. Now, since it connects to triple point to critical point, if you go along this line, we say we are now moving in the constant volume line, and that is nothing but the critical volume. And towards the left side of this curve, your V is less than Vc, and towards the right side of the curve is V is greater than, specific volume is greater than the critical volume. So, what we are trying to say here, that we are trying to find out here is that what happens to the slope of the curve. So, on this saturation line we say this dou p by dou t at constant volume becomes dp by dt, because at this point there is no role of specific volume, because it is a saturation line. And left side of this curve we say dou p by dou t at constant volume greater than 0, and dou p by dou t at constant volume is also greater than 0. So, what we are now going to see is that what is the basically the role of dp by dt is very important in deriving these Clapeyron equations. So, in our earlier relations we know that what is Sg minus Hf. Now, we can recall one of the Maxwell equations, dou S by dou V at constant t is equal to dou P by dou t at constant V. Now, here we will apply the simplifications, and since the specific volume has no role along this saturation line, so we can write this partial differential equation dou P by dou t at constant volume is replaced with dP by dt. This is a ordinary differential equation of the saturated line. Now, here the significant point is that if you are able to get, we can find the slope, and this slope will give you the change in the entropy with respect to change in the specific volume. So, further this equations is simplified to this form in a finite form, and when you equate both these two equations we get this Clapeyron equations like dP by dt saturated is into Vg minus Vf will be Hg minus Hf by T, and finally we arrive at a very fundamental relations, that is dP by dt saturated line. That means, if you want to calculate this value on this particular curve, we can easily find out from the values of enthalpy changes in the gas phase and liquid phase and specific volume in the gas phase and liquid phase. And since this phase change occurs at constant temperature, at that temperatures we have to take this value, that means slope can be easily calculated. And of course, this Clapeyron equations has a many significance, but apart from that there are some other kind of analytical representations people have made correlations. That means, people have developed the analytical representations in a logarithmic form. That means, they have assumed that as if this if you want to give more accurate results, that means if you want to increase your accuracy level, then you can involve multiple constants, that is A, B, C, D, and that means each stage you have to calculate these constant values and try to implement what is the relation between saturated pressure and temperature regions. So, basically this helps, this involves the constants that need to be determined empirically. But however, we will stick to the Clapeyron equations for our study only by these calculations, that is dP by dt on the saturated line will be Hg minus Hf divided by T into Vg minus Vf. Now, moving further, we are now going to get more information. That means, if you want to include more approximations onto the Clapeyron equations, then how it is going to change. So, basically Clapeyron's equations was suitably modified with two approximations. First is specific volume in the liquid phase is negligible in comparison to specific volume in the gaseous phase. In fact, if you recall our steam table data, that means if you have solved at UG level the data from the steam table, you will find that when you look at the data, we will see that gas phase has higher specific volume than the liquid phase. So, what this Clausius-Clapeyron equation assumes that the specific volume on the liquid phase will be negligible. And in fact, if you recall this pressure volume diagram for a pure substance, and if you look at this particular dome, and we have this critical point, and here we have liquid region and we have vapor region, and we are going during phase change, that means we are going inside the dome where both pressure and temperature is constants, and along the line your dou P by dou V at constant T is 0, and beyond this line this value is less than 0. So, what we are trying to say here is that if you go towards the higher pressure, and in fact these are the constant temperature line which we call as isotherms. So, constant temperature line, if you are talking about this as Tc, and at T is equal to Tc, this is the line. When the constant temperature line is drawn when T is less than Tc, this is this plot, and when the constant temperature is greater than Tc, these are the plots. So, these are basically the isotherms. So, in fact what we have done is this constant temperature lines on a PV diagram we have plotted, and accordingly the slopes also we can find out at the slope, that is dP by dV at constant T at critical point is 0, and above that it is less than 0. Okay. Then what this Clausius-Clapeyron equation assumes that specific volume in the liquid phase is negligible. So, basically if you drop a vertical and find out the value, we have Vf and we have Vg, and it says that Vf is much less than Vg, or Vg is much greater than Vf, this first thing. And if you are going for higher pressure side, that means if you are somewhere in this zone where Vg is much greater than Vf, which means that we are approaching to a gas side. So, whatever gas phase, now it can be approximated as an ideal gas model. So, when you have ideal gas model, we can write PV is equal to RT. So, as if we are saying your specific volume we are getting in terms of Vg, that means gas phase specific volume is represented in terms of temperature and pressure with an ideal gas constant value R, and this R value has to be chosen for water vapor. So, now when you make these approximations, we find the Clapeyron equations gets modified to another expression, we call this as Clausius-Clapeyron equations. We says that dP by dt saturated becomes Hg minus Hf. So, since the Vf is negligible, so it becomes T times Vg. So, this Vg we are replacing with RT by P. So, ultimately we get two expressions. One is dP by dt saturated is equal to Hg minus Hf divided by RT square by P. This is one expression, and if you rearrange these equations, then we can say d of ln P by dt saturated will be Hg minus Hf by RT square, and we have basically taken P to the other side. So, this is all about the Clausius-Clapeyron equations. Now, let us see that how this Clausius-Clapeyron equation will be useful to study the phase diagram. So, the name indicates the phase diagram means it is pressure temperature projections, and in these projections we have two distinct lines, one is fusion curve, other is vaporization curve, third is sublimation curve. Fusion curve separates solid to liquid, sublimation curve separates solid to vapor, and vaporization curve separates liquid to vapor. And the most important point is the triple point. So, wherever all these curves meet at one particular point, that point we call as a triple point. Now, let us see that how our Clapeyron equations is useful to study this phase diagram. So, let us first concentrate or locate a point A on this, maybe on the solid regions, and this curve is for water. So, I can say we can imagine some kind of ice which exists at point A, for which the temperature we can drop this point, and now if you heat this piece of ice at constant pressure, that means at constant pressure, let us say I am doing it at atmospheric pressure. So, 101,325 Pascal. So, if you keep on heating this ice at certain temperature Ta, and keep on heating, slowly we will be moving towards the fusion curve, and we will arrive at a point which is called as a melting point, and here I will refer as the NMP, that is normal melting point, is normal melting point. So, why I am saying it this normal melting point, I will give its significance later, okay. And this normal melting point we means that this is at constant pressure, okay. So, that is the word which is referred as normal melting point at constant pressure. So, basically when ice is heated, its temperature is increasing, and this heating takes place at constant atmospheric pressure. So, we reach this fusion curve, and if further heat is added, the ice becomes liquid, and when ice become liquid, at that point of time there will be no change in the temperature. But when the ice melts completely to liquid, then the liquid with addition of heat, liquid temperature further increases and we move to the point B. So, the final point will be TB. So, basically in one way I am saying that at the constant pressure heating changes the state of the ice from point A to point B. Now, let us see, and at that point of time we say that we are reaching this normal melting point which is called as TNMP, and ultimately what we can say is that when enough heat is added and ice melts completely, the state of the systems moves from fusion curve to the vaporization curve. In other words, we can say that this normal melting point whatever we have defined, that means the sample of ice at normal melting point coexists with what? Water which is in liquid state, air which is at standard atmospheric pressure. Now imagine a situation that I am doing this heating with change of pressure as well. So, in the same situation was modified little bit and tried to see how we are going to show it in the phase diagram. That means when a sample piece of ice is placed in a chamber and the air pressure is lowered, that means that chamber is designed in such a way that we can control its pressure, and when the air pressure is lowered, the state of the system will no longer be fusion curve. Ideally point A would have gone to this normal towards the fusion curve, but what I am doing, since I am changing this pressure, so not necessarily that I will be moving to that. So, basically as a result of the change in pressure, the temperature also will change by delta T. That means I can come back, instead of going from this, if I draw a point here, so I can find out what is delta T and what is delta P. Delta P is in our control, and we can see that when there is a drop in pressure, the slope of the fusion curve, that means if you draw this particular points on the fusion curve, the slope of the fusion curve will be negative, because the decrease in the temperature will result in the increase in the melting temperatures, and the slope of the fusion curve is negative. This is for specifically for water or substances like graphite and bismuth which expands during freezing. But for all other substances the slope is positive, that means for which the decrease in temperature results in the decrease in the melting temperatures. So, although we know this fact in our earlier thermodynamics course, but here we try to link up that how this property relations helps to justify our stance or whatever you have observed that is true. So, same thing we can recall here to study this Clapeyron equation here, because all these things that we need is the change in the pressure and change in the temperatures, and it is happening on the saturated line. So, we can find out, use this Clapeyron equations dP by dt at saturated, dP by dt for this saturation situation, and that is nothing but Hg minus Hf divided by T into Vg minus Vf. So, this dP by dt we can discretize in the form of delta T. So, delta T by delta P you can represent in this, and this will give you change in the temperature, okay. And this change in the temperature of delta T, which occurs at, which is a function of the specific volume difference and the enthalpy difference, and this occurs at the temperature T, because this phase change process is occurring at particular temperature. Okay. So, ultimately the conclusion that we derive from our analysis for a phase diagram is that the negative slope of the fusion curve of water emphasizes that the triple point of water, which is 273.16 Kelvin, is higher than the normal temperature, normal melting temperature, that is 273.15 Kelvin. Now, what is the significance at normal temp melting point and triple point? At normal melting point, we say that ice, water are in equilibrium with air at pressure 101,325 Pascal, that means it is with atmosphere. While at triple point, ice and water are in equilibrium with water vapor, which has a vapor pressure of 612 Pascals. So, you can see that how a drastic reduction of pressure happens at the triple point, and because of this there is a, since there is a depression in the triple point value. So, we call this depression as a phenomena we call it as resolution, which means it is defined as the phenomena for any pure substance, in fact with those pure substance that expands on freezing. This pure substance melts under pressure. So, these substances melt under pressure and again freezes again when the pressure is released. So, as if they behave as in an elastic and situations where they expand and again then they melt first and then again freezes again when the pressure is released. So, such a phenomena we call as re-resolution. Now, the other significant part for this pressure temperature diagram is nothing but we have the sublimation curve and vaporization curve, and for both the curves the characteristics features are typically not complicated. So, here it is not like fusion curve, and in this sublimation and vaporization curves the slope is always positive because the molar volume of vapor is always larger than the molar volume of liquid. And of course, we all know that increase in the volume of sublimation that suggests that vapor has more disorder than the solid or liquid. So, means that entropy plays a role. So, the entropy transition from solid or liquid to vapor is always positive, and this entropy calculations we can calculate from the Clausius-Clapeyron equations which is derived earlier and through Maxwell equations and Clapeyron equations. So, this is all about the concept of phase diagrams based on the thermodynamic properties relations. Now, with this background, let us try to solve some numerical problems, and this numerical problem is nothing but we need to justify the property data from the pressure, temperature, volume, pressure, specific volume and temperature data for pure substances, and in particular we will recall with water. In the basic thermodynamic course, the data or steam table data has been exhaustively used, but here we will try to link up how these data are generated and how they, and when you say for a given pressure, temperatures, we find SF, SG, VF, VG, enthalpy, internal energy, how they are calculated. They are nothing but calculated, but actually these are derived data, and in fact thermodynamic property relations helps us to derive these data. Now, in this numerical problem we try to see that what is the significance or role of these thermodynamic relations in the formation of steam table or any property data for pure substances. So, with this background, the first problem talks about the saturated water which is available at 100 degrees centigrades. Okay. Now, it is very clear that when you we say saturated water at 100 degrees centigrade, so we can use this steam table or the property data for water, and from this we we can easily find out the enthalpy, internal energy and entropy. So, let us find out, let us recall that these values at 100 degree centigrade we can find out Hg, because we require the change in the enthalpy, that means Hg minus Hf is 2257 kilojoule per kg, then Ug minus Uf will be 2087.6 kilojoule per kg, and Sg minus Sf is 6.048 kilojoule per kg Kelvin. Nothing to worry, because any steam table data will give you this value, or any thermodynamic book will give this value, but there is nothing new in it. But what is new in it is that we wanted to see how whatever equations we have derived so far, how those equations can be used to find this value. And here we will see one thing that we require information is, these are actually the calculated data. And the measured data, we can say that we can also find out what is Vg is 1.673 meter cube per kg, and we also have Vf is equal to 1.0435 into 10 to the power minus 3 meter cube per kg. Since it is the specific volume, we can say it is a measured data. Why I say measured data? Because normally pressure, temperature, density or specific volume are considered as a measured data. Now we need to recall this Clapeyron equation. We says that Hg minus Hf is equal to T into Vg minus Vf into dP by dt, saturated line. So basically, to calculate this enthalpy change, we require Vgm and Vf. Temperature we know, that is 100 degree centigrades, and what we do not know is dP by dt at saturated, slope of this dP by dt curve. So to do that, we can take some data sheet, like we can say saturated pressure and saturated temperature, or I will say P saturated in bar, T saturated in degree centigrades. So we can get the data, or we can measure the data at different temperatures. Since we require at 100 degree centigrades, let us start some value from, maybe starting from 50, 60, 70, 80, 90, 100, 110, 120, 130. I think this should be sufficient to get a set of data, and corresponding pressure value we can note it down as for this we can again refer the steam table, like 0.1235, then 60 degree centigrades we have 0.1994, 70 degree we have 0.3119, 80 degree 0.4739, 90 degree 0.7014, 100 degree we have 1.014, 110 1.433, and 120 1.985, 130 2.701. So basically dP by dt can be calculated from any these states, and one way to do this is that we can plot it graphically. P saturated, T saturated. We can start with maybe 50 and end with 130, and with different intervals 60, 70, 80, 90, 100 like this, and accordingly we have pressure values So, a plot can be done. Upper limit of pressure is 2.701 and at 100 degree centigrade somewhere here, if you drop a vertical, it touches this curve, and at that point we can draw a tangent, and at this point we can find out dP by dt saturated, and from these calculations we can find out this number as 3570 Newton per meter square Kelvin. Now once I know this, and obviously we can go do calculation one by one. So Hg minus Hf would be T is 373 Kelvin, Vg minus Vf 1.673 minus 1.0435 into 10 to the power minus 3 into this value 3570. So we get this number 2227. So we recall this is 2227, but actual value is steam table data is 2257. So that means Clapeyron equation is accurate by 1% less. Okay, and once you know enthalpy, we can find out internal energy Ug minus Cf, that is nothing but Hg minus Hf minus P into that is saturated into Vg minus Vf. So Hg minus Hf is known 2227, P saturated value 100 degree centigrade is 1.014 into 10 to the power 5, Vg minus Vf is 1.673 minus 1.0435 into 10 to the power minus 3. When you put it, this Ug minus Uf would be 2086.5 kilojoule per kg, but actual data is 2087 or steam table data is 2087.6 kilojoule per kg. And last part is entropy. So Hg minus Hf would be Hg minus Hf divided by T. So it is 2227 divided by 373 Kelvin. So this number is 6.046 kilojoule per kg Kelvin. So of course this value is close to 6.408 from the steam table data. So this demonstrates how this Clapeyron equation is useful to get the thermodynamic properties value, and in particular we have validated it with respect to the steam table data. Now another important significant point that I need to emphasize in the second problem is the phase diagram. So basically we want to demonstrate, I have been talking about the change in the pressure delta P with respect to delta T on a phase diagram when we are moving along a fusion curve and the pressure and temperature changes simultaneously. Then what happens? So calculate the change in the temperature when its pressure is increased from vacuum. Vacuum means it is initially at zero pressure for triple point to atmospheric pressure at normal melting point. So data that is given is 273 Kelvin, because at that particular point is 0 degree 273 Kelvin means 0 degree centigrade. The specific volumes of liquid and vapor are represented in the meter cube per moles, okay, and enthalpy changes are also noted down 6.10 kilojoule per mole. So just want to signify that if you recall the Clapeyron equation, we says that dP by dt saturated is equal to Hg minus Hf divided by T into Vg minus Vf. Now here we will be trying to represent in terms of dP and dt. So I will rewrite this equation as delta T is equal to T times Vg minus Vf into delta P divided by Hg minus Hf. Now data that is given, we know that this is given at 273 Kelvin T. That means the phase change occurs at 273 Kelvin. And that point we have data Vg as 19.64 into 10 to the power minus 6 meter cube per mole, and at Vf is 18.02 into 10 to the power minus 6 meter cube per mole, and the enthalpy change Hg minus Hf data given Hg minus Hf is 6.10 kilojoule per mole. Now by inserting this value in these equations, we can find out, you can see here, sorry, vapor is this. So data that is missing is this value would be liquid and this is vapor. There is a correction. So I think since there is a slope is negative, I think that data was interpreted wrongly. So delta T would be, T will be 273, Pg will be 18.02 minus 19.64 into 10 to the power minus 6, delta P is, that means atmospheric pressure. So P atmosphere is 101,325 Newton per meter square, and since starts from vacuum, so delta P is nothing but delta P, P atmosphere. So you can write this as P atmosphere 101,325 divided by Hg minus Hf 6.1. So 6.10 into 10 to the power 3. So after getting this, we will say delta T would be about minus 0.0073 Kelvin. So what is the significance of this number? Means that the increase in pressure depresses the triple point by of ice by minus 0.0073, or we can say depresses by 0.0073 Kelvin. And this happens because one is we have normal melting point and other is triple point. Ideally it should have located at this point, but due to this pressure change it is getting located little bit lower than the normal melting point in this fusion curve, and this difference is 0.0073 Kelvin for this data. So with this, let us close this lecture today. Thank you for your attention.